I just eliminated the screen there. Okay, thanks, Anna. So today, can you guys see the screen here? Okay. So today I'm going to explain what's going on with this paper with Mellett from 2021, I think, called A Combinatorial Formula for the nabla Operator. So maybe one thing about the title. So usually it's, you have this this nabla operator, and usually you're interested in, you apply nabla to something like, say, the elementary symmetric function, and then you'd like a combinatorial formula for the result you get. This is called sort of a combinatorial formula for the whole nabla operator. And so the reason is that the main formula for this paper is a formula for all the matrix elements of the nabla operator in a particular pair of bases. And so the idea is you can in principle, you could take this instead as a definition of the nabla operator, because it would characterize it by the formula, which wouldn't be the case if you're applying it to a particular symmetric function. So another thing here is this combinatorial formula for nabla. This is also a little bit of a reference to the paper, combinatorial formula for the McDonald polynomials, which is Jim and Mark Heyman and Nick Lower's paper. And so the reason there's this reference there is that we give two proofs of this main formula. One of those proofs is in the same style as the proof in that paper of the formula for the McDonald polynomial. So namely, the McDonald polynomial is defined by axioms. I mean, it's the result of doing the Gram-Schmidt algorithm, basically. And so one of the proofs of this thing is to establish the candidate formula for the nabla operator and show that it satisfies the triangularity, diagonal term, et cetera. So it's the same type of proof that you would do, which you couldn't do if it were just a formula for the application of one particular symmetric function. Okay, so here's what I thought I'd do for the order. So first, I'm just going to explain. So what does the formula say? I have to show you a couple notations. Actually, it's a little confusing. It's an elementary formula, but it takes a minute to unpack. And then the second thing I wanted to explain, which is sort of where does it come from? So in other words, how might you guess this? Yeah, how does one guess the formula before going about proving it? And then I'll explain some special cases. So how you can recover some of the previously known identities involving the nabla operator from that formula. If you sort of start with this kind of thing, you can, specialize one variable to be P1 to the n, and you get one thing. You might take some plethism and you get a different thing. And so I'll list what you can get from those special cases. One of them being a new proof of the shuffle theorem. So this is one thing you can extract from this formula. And then four, and this will probably be next time. And so this is the geometry / affine Springer fibers. So next time I'll explain what this, how this relates to geometry. So it turns out there's one interpretation of this formula, which is that it's actually encoding the equivariant Borel-Moore homology of space, which is the affine Springer fiber. One of the nice things about this particular affine Springer fiber is it happens to be Goreski-Kottwitz-McPherson space, which means basically the presentation of its equivariant cohomology ring is very explicit. And so you can explain how would you do this using Grubner bases and things like that without really referring to the space. Okay, so first thing. Wait, where's my? Here we go. anti-erase. Here we go. Sorry, I kind of updated when I loaded this thing, it kind of updated the whiteboard thing. And now I can't seem to.
Is it possible to lasso that, like on the right-hand side, that's the dotted line, and then just select everything and delete if you want to?
Maybe. Let's see. Lasso and the.
That's, I think you're in pen mode still.
I am. Yeah, I'm sorry about this. I haven't
No, you're
used this in a
fine.
while. It kind of updated the software here. It all looks different. Oh, here. Okay, good. Okay, I'm not going to erase. I'm just going to push it all out of the way. Okay, so first of all, let me explain what this formula says. So let's take this. Let's start with this. The nabla operator. So this is the map from symmetric functions in a set of variables. So I'm going to use capital X to itself, and so sim k of sub qt of x. So this will be the symmetric functions over the field of rational functions in two variables, x, q, and t, with rational coefficients in some set of variables. I'll call it capital X, and there's infinitely many variables, as usual. And the definition is that it is the operator that sends the modified Macdonald polynomial to power of q and t, where n is this n is the statistic from Macdonald's book. So to give you an example, so let's go over to my Emacs window here. So for instance, if I take modified Macdonald polynomial like that, right? So this is the modified Macdonald polynomial 3, 1 in the Schur basis. If I apply nabla to that guy, I'm going to get something else. If I expand this back into the modified Macdonald basis, it just multiplies it by those numbers in Q and T. On the other hand, if I apply it to, let's say, E4, I would get some expression which looks like the QT parking functions, but the whole Frobenius character. And so now what I'm going to do, so the formula is, instead of applying this to EK, I'm going to apply it to symmetric function in 2n variables. So I'm going to write down a symmetric function, which will be En, and then I'm going to plethistically substitute into En two different sets of variables. Call it X and Y. And so what this notation means is this is this usual plethistic substitution operation. So this is the thing where if I evaluate this, this is the same thing as evaluating En in infinitely many variables, and then substituting into each one of those variables xi, yj, q to the k, and t to the l. That makes sense. So said another way, for instance, if I took En of just x over 1 minus q, this would be the same thing as En of x1, x2, dot, 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 x1q, x2q, dot, 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 x1q squared, etc. And this is also the result of starting with En and evaluating it at the operation which sends the power sum generators of the symmetric functions and evaluates it at pk over 1 minus q to the k. Okay, so if I do this, so this particular thing, this, you might also recognize that this is the expression for the Cauchy product for the modified Macdonald polynomials. So another way to say this expression is that this is the sum over all for all mu of h mu tilde of x, h mu tilde of y, and then divided by the norm squared of h mu tilde, which is also given by the product over all boxes of 1 minus q to the power of the arm length. Okay, maybe I won't bother writing this whole thing out. Leg length, etc. Right? So this denominator, this is the inner product of h mu with h mu in the Macdonald product. Okay, so far so good? Okay, so now I'm going to explain this formula. So main theorem. So what this says is that if I take the nabla operator to the power of k, and I apply it to this expression, I'm going to give an explicit combinatorial formula for this guy. And so first of all, what I mean by this, so this thing that I'm applying nabla to, so this is really, this is a symmetric function in both the x variables and the y variables. And so what I mean by this nabla operator is just the nabla operator in the x variables. So I expand this as I can take an expression like this, I can expand it into, as a linear combination of symmetric functions of degree n and x times a different symmetric function in degree n and y. And then I would just, on the x component, I would apply the nabla operator. And so if I can write down this expression, because I've also got this y variable, this is basically equivalent to writing the nabla operator in the sort of, you might call the modified elementary to monomial basis. So the point is, this sort of this has in it all the different coefficients of the nabla operator, because I've kept track of what I applied it to with this separate variable, which is y. Okay, and so now here's the expression that's in this paper. So on the right-hand side, I'm going to take a sum over several terms. I'll explain what this brackety thing means. And what goes here is, so I'm going to write this as ought q so I'm just kind of writing it down first, and I'll explain what all these things are afterwards. It should say div. And then I'll say x to the a, y to the b. And so what this is this is a quasi-symmetric function type expression for this, for the nabla operator applied to this expression. So in particular, I'm claiming that the sum, which I haven't explained yet, is going to end up being a symmetric function in both the x and the y variables. And as usual, it's something where it's not obvious that it looks symmetric, but once you relate it to LLT polynomials, then it becomes clear that it is. Okay, so let's unpack this guy. So first thing is M. So M is an element which is just a vector of non-negative integers to the n. So M is an n tuple of non-negative integers. A and B are both compositions. So in other words, they are n tuples of positive integers. X to the A, as usual, this refers to x to the A1, x to the AN. So in other words, the elements of A encode the labels of the variables x. And so if I write x subscript A, some papers, people write it as a superscript. I usually like to write it as a subscript because they are the subscripts. And so this is just the product of the x's with those labels. So for instance, if I took A is equal to, let's say, I don't know, 1, 2, 1, 1, 3, then x to the A would be x1 cubed, x2, x3. So that is M, A, and B. The norm of M is just the sum of all the elements of M. And so that explains all the variables. And so now what's left is I have to explain those, what I mean by these brackets. What is this automorphism factor and what is div? And then maybe I'll stop and do an example. So these brackets, right, the bracket of something like M, A, and B. So what this means is this is the sorted representative of the triple MAB in the left coset S of right. So M lives in this thing. A and B both live in this thing. So M is here, A is here, B is here. And so now I have an action of the symmetric group Sn on that product just by acting diagonally. So in other words, just simultaneously exchanging the corresponding elements of M, A, and B. And so what this square bracket thing indicates is that first of all, the sum is over just representatives of that left coset, and I'm always representing that coset by a triple which is sorted in the following order. So the triple in these brackets is sorted according to one, the reverse Lex order in M. So M is always going to be sorted in decreasing order. 2, the usual Lex order in A. To break ties between the two M variables. So if I'm comparing, in this order, if I'm comparing MAB with M prime, A prime, B prime, I would first just compare the M terms, check if they're, sort those in the Lex order, the reverse Lex order. If I get the M prime equals N prime, then to break ties, I would then proceed to the A's, which are sorted in the usual Lex order, and then the same for the B's. Breaking ties in both M and A. Okay, so that's the sum. That's what the sum is. So this is over just those left cosets. The next thing I've got is this DIN statistic, and then I have this automorphism factor. So my automorphism factor is just the following guy. So it is the product product over all I of the Q factorial of alpha I, where alpha is the composition, which is the level sets. So what I mean by this is that if I took, let's pretend I didn't have a B factor, just to keep it kind of short. Let's say I took alpha of something like 2211110, and then let's say I took A is 1 1 say 1 2 1 1 1 and then 2. I'd be looking at the composition, which is 1 1 3 1, because I'm breaking this up according to which pairs mi comma ai are equal, right? And so in the first block, we have 2 1, right? The next, this is sort of easier to write this in as a matrix. So let's say I wrote it like this. So this is 1 1 3 1, because this pair of numbers is different from the next pair of numbers. The m's are the same, but the a's are different. This pair is different from the next pair, but then I have a block of 3 in a row that are all identical. And then the last one is just in a group by itself. And so the automorphism factor is just the product of those sizes in the corresponding composition. Okay, then I have one more thing, and then I'll just sort of forget about the formula. So DIN of a triple in this case, and this will be a little bit more meaningful later, but for now I'm just writing down these definitions. It looks like a lot of other DINs. So it's the sum over all I less than j of mj minus mi plus 1 plus k. And then I'm going to say the function, which is 1, if ai is greater than aj. So in other words, an inversion in A. And then plus 1 if I have an inversion in B. And then I take that entire expression and I take the max of that thing with 0. This guy could potentially be negative, and I just cut it off and take the max with 0. And so I get a non-negative number. Okay, so there, I just kind of wanted to write the whole thing down just so I have the notation first. It just looks like a formula, can't really make much sense of it. But maybe now is good time to ask, are there any questions so far about this expression? Or okay, so let me do an example. So let's go over to this sort of maple type window. Oops. So here's what this looks like. So let's say I took the first expression. So what would nabla of en of x over y look like? So if I type this in maple, let's type in something like 3, 2. And so in my code, so first of all, well, there's lots of equations, so I just call it equation 7. And so this is in this notation here. So this is k equals 1. And so this is that left side expression. So this is applied to E3. The first number is n, which is 3. And so this is nabla to the power of 1 applied to E3 of xy over 1 minus q, 1 minus t. And then that second number 2 is, because the answer is an infinite sum in the t variables, to get a finite sum, I have to ask for a particular power of t. And so since it's explicitly expanded in powers of t, that second number is just the exponent in front of t. And so what you get is just a slight extension of this Stembridge's maple package. Some of you might recognize the Schur function kind of notation. With the one caveat that I've now got something like Schur function, not just 1 and 1, but Schur function of x. Right. And so this is a sum of expansion in the Schur function in x tensored with Schur function in y basis. And so these are the coefficients. And so the first equation 7 of 1, this is gotten by just applying the nabla operator as usual to that expression. And so here you see these interesting kind of automorphism guys. On the other hand, can also take equation 7a, which is the notation for the right-hand side of the theorem. And so now we'd like to confirm that that's the same thing that we get from this expression. And so in the right-hand side is really given in terms of the monomial symmetric function in both. And so what I can do is I can extract, so this is written in the Schur basis, but I can extract the coefficients in the monomial basis. And so what I'm telling you, let's go back up here, is if I took this expression, I converted both x and y to the monomial basis, and then I took the coefficient of 2, 1, and then 1, 1, 1 in y, this would be the coefficient, as you can compare and check. And so one thing you notice is that if you run the second equation, it's actually much faster. Applying nabla is kind of time consuming, but if you just have a sum, you write it and it just, it's quite a bit faster. And so what's listed here is all the triples of M, A, and B. So as I'm adding them up, I had to print them out so you can see what they are. And so you can see that they are all in order, right? So the M is always in decreasing order. And A is increasing whenever you have ties in the M, right? So A is allowed to decrease here because M was not the same across those two terms. Okay, so that's what this sort of thing looks like. So if I compare all the coefficients, you can run it up to n equals 7 or something and check that, see that all the equations are the same. Okay, so let's go back here. So this is the formula. So now what I'd like to do is explain where does this come from? At the moment, it's just sort of an expression that looks a lot like the types of formulas you get in this subject, but doesn't really mean anything yet. But so I want to explain first of all, why do I know this is symmetric function? So one has to do the usual thing where when you have an expression, a quasi-symmetric type expansion, you have to show that it's symmetric. And I want to show where does this come from? So how is it generated? And then I want to show some examples of what you get if you specialize this in different directions. Okay, so first of all, what's the motivation? I'll say motivation, by which I really mean how is it? How would you guess it on a computer? So here's the idea. So first of all, the meaning of the left-hand side. So is that this actually has an interpretation in terms of Haymann's theory. So if I take the theory of coherent sheaves on the Hilbert scheme, and so the interpretation of this thing is that this thing is also equal to the Frobenius character. Next line. Of the sum over all I greater than or equal to 0 of the derived global sections. So it turns out I actually don't have to say derived, but I'm just going to write it like this at first. So the derived global sections of the sheaf on the Hilbert scheme, which is the Procesi bundle, tensored with its dual bundle, tensored with O of K. Okay, so what do I mean by this? So first of all, this is the global set. So this is a space of sections of 3 different bundles on the Hilbert scheme of points in C2, of endpoints on C2. So this is Procesi. This is Procesi. And this is the line bundle, which is the determinant of the tautological bundle, which is B. Okay, so this is the Procesi bundle, is the rank n factorial bundle. That comes up in Mark Hayman's theory of sections of from this paper in Invenciones about character formulas and spaces of sections of bundles on the Hilbert scheme. So every one of these is a bundle. And I won't have to say Hilbert scheme in a second. I'll give you something more explicit. But these are all bundles on the Hilbert scheme of n points on C2. So the idea is, in the same way as in that paper, you can calculate this expression using a T-Abat localization. And so if you write down this expression, this is precisely what you'd get if you took this symmetric function in 2n variables and then took the Cauchy expansion and then applied nabla to the McDonald factor. What you're getting in that Cauchy product that I wrote down above, if you insert this nabla operator, you're precisely getting the T-Abat localization expression for this Frobenius character. So, and it turns out that actually summand here is always going to be 0. Oops. Unless I equals 0. So in other words, there are no higher derived functors here. And so in fact, this whole expression is just the space of sections of that bundle. So in our paper, this is left as a conjecture. So this sort of statement that the only term that contributes is the 0th term, this is the type of thing that's proved in Mark Hayman's paper from before. So for instance, you'd see a statement a lot like this in the situation where you have Procesi bundle times the tautological bundle B to any power L, but just one copy of the Procesi bundle. Then it's crucial theorem in there that in fact that space has no higher derived functors, and so you can describe its space of sections as an explicit type of module, which is called the polygraph type module. And so now what I'm saying is the same is actually true, the same statement is true for these bundles. And so so in our paper, this is left as a conjecture. We didn't know why this was true. It did not follow from that original paper, but if it's true, we could you can use it to generate conjectures about the combinatorics. So it's just sort of assumed that it's true and left as motivation. But this actually was proved since then.
Question here.
Oh yeah, yes.
Yeah, Is a determinant part determinant of B? Is it explicitly computable or just not?
It is. So it's the thing. So it's the line bundle, which so you imagine. So I'll describe it in the fixed point basis. So the fixed points of the Hilbert scheme are the partitions, and the character of that line bundle restricted to one of those partitions is exactly the factor from the nabla operator, which is q to the power of n of mu and t to the power of n of mu prime. So I mean, so in other words, that would say, so computable, and so that would be its restriction to any one of the fixed points.
Okay.
And so, right, so it's like, so yeah, I should say what all these, this is useful. So what, just to say something about these bundles, right? So the Hilbert scheme has this torus action. The fixed points, right? So the Hilbert scheme is the set of all ideals in C of X and Y with the property that the dimension of the quotient just as a vector space is equal to n. But then there are these special ideals which are generated by monomials. And what these bundles are is they're the ones whose restriction by the proof of the n factorial theorem, the Purchase bundle restricted to mu is the Macdonald polynomial. B, the restriction of B is the sum of the boxes. And then the restriction of this line bundle is the product of the boxes. And so let's see, where was it? Oh, yes. And so what I was saying before is that this actually vanishes. This is left as a conjecture, just as motivation in our paper, but this statement was proved by later by Losev and Alvarado. Doesn't follow from the original papers. And so now I should say what I mean by this Frobenius character here. So each one of these bundles, P, P star, and O to the K, so these are three different bundles on the Hilbert scheme. Both P, and so also its dual, they're rank n factorial bundles with the property that the fiber over every point of the Hilbert scheme carries an action of Sn. And so this Frobenius character is sort of a Frobenius character of a bundle with two separate Sn actions. The Frobenius character takes an Sn representation and gives you a symmetric function. So this is going to be giving you two different symmetric functions. And the two different factors of P and P star correspond to the two different sets of variables, X and Y. And so the character of the statement is that the character of this whole thing is equal to this expression. So the use of this in terms of generating formulas is that now I can turn this thing into an explicit vector space and then search through that vector space for bases and use that basis to conjecture the formula. And so that's how one discovers, gets a computer to predict that right side. You then have to figure out what these automorphism factors are, but it's sort of experiment and trial and error. And so here's what this thing is as a space. I'm going to give you something much more explicit. So this, I described this nabla of this elementary symmetric function as the Frobenius character of a space of sections of a bundle on the Hilbert scheme. And now I'm going to give it to you as something a much more explicit module over a pair of variables. So let's take the ring of symmetric functions, or sorry, the ring of all polynomials in 4n variables. So I'm giving an explicit description in the same style as Haymann's polygraphs ring, but for that set of for that bundle, P times P star times O of K, instead of the one that appears in Haymann's paper, which is P times B to the power of K. And I'm giving the polygraph type presentation, but instead for this bundle. And so here's what this looks like. So each one of these variables, first of all, I'm putting a bar over it. Each one of them has n different variables. So I've got x1 through xn, y1 through yn, z1 through zn, w1 through wn. And now what I'm going to do, and by the way, I'm using lowercase letters here, so these are not to be confused with the capital X and capital Y. So these sets of variables are completely separate from those. And now what I'm going to do is I'm going to take a map, pi, which is a map of C of X bar, Y bar modules. Into the free module, which is the direct sum over all permutations in the symmetric group Sn of the free module over just the X and Y variables times a placeholder, which I'm going to call E subscript sigma. So in other words, I'm mapping this guy into the free module over C X bar Y bar with one generating basis vector for each permutation sigma of n. And that map is the one which sends F to the sum over all sigma of F of X bar, Y bar, X bar sigma, and Y bar sigma times E sigma. So in other words, so pi is going to take any polynomial in 4n variables, and it's going to send it to the element of this free module where the coefficient in front of a permutation sigma is the result of applying F, first of all, just to X bar and Y bar, but then evaluating the Z and W variables at X bar and Y bar, but then permuting the ordering of those variables according to sigma. Okay, so this is pretty clearly, clearly a map of modules over X bar and Y bar. And so I can ask, what is the image? And so the image of this thing, so I'm just going to call this M. And the statement is that M is actually the space of sections over the Hilbert scheme in the same style, in the same sort of way that Mark Haymann's polygraph paper describes sections of one Purchase bundle times powers of the tautological bundle in terms of polygraphs. This is sort of a similar statement, but for Purchase bundle times L. But with K is equal to 1. So I'm just taking the K equals 1 case to keep it simple, but there's a family of modules, these polygraph type modules over C of X, Y, one for each power of K. And I'm just writing the case of K equals 1 to keep it simple. And so therefore, putting this all together with the previous statement is that the nabla operator, just to the one power of En of xy over 1 minus q, 1 minus t, is equal to the Frobenius character of M, where M is being, where M is now just thought of as a bigraded vector space graded in the Q corresponding to the X bar variables, Y corresponding, or T corresponding to the Y bar variables. And so it's a bigraded SN cross SN module. And so the two different SN actions is, first of all, I have the left action. So the left action of SN acts, first of all, internally by automorphisms of the ring C of XY, and then by multiplying E sigma on the left. Right, so let's write it like this. So left action sigma times F of X bar Y bar E sigma, let's use tau, is equal to F X bar restricted by sigma, Y bar restricted by sigma, times E sigma times tau on the left, and the right action is given by F bar E sigma times sigma on the right is simply the result of multiplying tau on the right. So only the left action acts internally on those variables. And so the statement is that this module, which is the image of that map, has the property that has these two different SN actions. It's got two gradings, and the Frobenius character is this expression. And so therefore one can use this to sort of search for combinatorial formulas by searching for bases. And so now I'm going to state, how would I go about predicting? How do I predict formulas? By way of M. So let's start by just forgetting the SN action, right? So I can, so here's one way of predicting formulas using M. Consider filtration of the original ring, which is C of X bar, Y bar, Z bar. Be the span of all X, Y, Z times W to the A. Sorry. W to the B, as B ranges over all those integer vectors, which are less than or equal to A in the Garcia-Stanton descent order. So in other words, the ordering for which B is less than or equal to A if, number one, I sort B in reverse order, and this is less than or equal to sorting A in the Lex order, should be less than, right? And so then to break ties, I would simply compare B and A directly. So in other words, choose the ordering on the monomials, which is the Garcia-Stanton descent order, and it's defined by first, you don't just compare them in the Lex order, you start by first sorting them in reverse order, basically giving you partitions. You then compare those partitions in the Lex order, and in the event of a tie, you compare the original vectors. And so the statement is, if I write down this module, so I filter by those things in the W variables, then I claim that if I take the corresponding filtration on M by just taking the image of FA, and I take the subquotient, just say character. So if I take this ordering that I gave you, this Garcia-Stanton order, I take the image of that filtration in M under the map pi, and then I take the subquotient Fm modulo Fm minus 1, and minus 1 just means take everything below it in the total order. If I take that subquotient, I claim that this thing is actually the contribution of the number. This is the contribution coming from M. In that combinatorial expression. And so basically what you can do is in the computer, if you can do some Grubner bases and get it to output those Frobenius characters, what you have to do is just sort of guess. You can generate the formulas that you're looking for, and you can use that to guess the formula. And then sort of the tricky part is using that to guess those sort of automorphism factors. And so this is how you predict formulas. So what this has to do with, so this strategy, this comes from a paper with myself and Alexio Blomkov. And so the strategy for generating formulas is applied there to the diagonal co-invariant algebra. And so the statement is this Garcia-Stanton descent order, which turns out has a geometric interpretation, which I'll explain next time. You can use this to, in some cases, you can use this to sort of predict formulas of this sort of DINV type. So this is maybe this is the answer of how to guess Formula One. Okay, let's see. So maybe so now I guess we're at the next point. So are there any questions so far? Okay, so so at this point, so the strategy is this formula comes, so this is how one might predict this formula. And then once you have it, the strategy for the proof, or one of the two proofs that we gave in that formula, is once you've guessed the formula, you have the candidate, you simply show that it satisfies let's give this thing a name. So let's say I take this right-hand side and I call the right-hand side, we called it omega. proof strategy. Show that omega k xy satisfies the axioms of the nabla operator, which is to say that it's for instance, triangularity in the dominance order, etc. Let's see. So I wanted to say some special cases. And I think I have, it's an hour, is that right? So I have about 5 minutes left. Okay, so next time I'll explain what is going on with the geometry here. But just to give a preview. Is that this module M is isomorphic to the equivariant Borel-Moore homology of a space which is the unramified affine Springer fiber studied by Goreski, Kotwitz, and Fearson. And so this is a space whose equivariant cohomology and Borel-Moore homology groups have an explicit presentation. So you can, this is not always the case about, spaces in this subject. I mean, there's, but this very particular type of affine Springer fiber has the property that you can actually just build its space explicitly using the GKM relations. In other words, it has an explicit presentation. So there's two points here. So the first is that M is isomorphic to the Springer fiber. And the second is that Frobenius character of the Springer fiber is equal to omega. And so this statement, this was also kind of conjectural in that paper, but this also, so this is proved in that same paper by Losev and Alvarado. And this statement is proved in a second paper and this is done by explicitly counting Schubert varieties in this space and comparing those, comparing the sum that you get from adding those things up to this combinatorial expression for omega. So this is in the same way that, for instance, if you look at formulas of the type that Hikita looked at, in which you can interpret sort of DINF type sums in the subject as a kind of graded count of Schubert varieties in a certain affine Springer fiber. This is a parallel sort of statement to that one. So what you check is that this expression for omega, sorry, once you account for the symmetric group actions, you are actually counting cells in a particular type of Springer fiber too, and you can just compare those two things directly. And so next time I'll start by saying, so I'll talk a bit about this geometry. I'll also explain some special cases. So if I specialize Formula 1, I'll say which specializations lead to some different, how to recover sort of different types of formulas, for instance, the shuffle theorem, and also Also some other formulas. For instance, there's another formula by Elias and Hogenkamp you can get by sort of specializing in a different way. And also the specialization that you'd use in order to prove the axioms of nabla, so the one that you'd use to actually prove the statement. And then let's see what else. Yeah, so next time I'll go into those special, yes, and also I'll explain what this has to do with something called the Hessenberg paving. In GKM theory, and also as a consequence of that, the statement of why is omega at least a symmetric function. So at the moment, it's sort of a quasi-symmetric function. And so this will also prove why do we at least get a symmetric function in the first place, which of course you always have to do first. Whenever you have an expression like this in the subject, you have a quasi-symmetric function type expansion, you always have to first show why is it at least a symmetric function. And so that turns out to be related to this thing called the Hessenberg paving, because what that paving leads to under this equality is it leads to an LLT expansion of that omega operator. So you basically just relate it to the original LLT polynomials. Okay, so I think that's what I wanted to say today. So next time we'll start, and I'll should be a little more motivated. I'll start with geometry, and I'll explain those spaces and how you would count cells in them, and also generate these explicit homology presentations.
Thank you so much. Let's thank the speaker. Thank you. Very nice. Any questions? So I have a very short question. I'm just wondering, like, because nabla of En can be looking at the just parking functions, and you have like this. This is like a more general version, and I know that like you have some type of theme statistics, and I just wonder, like, is there any combinatorial objects that arise from this, like dict path like, or parking function like, or tableau like combinatorics that is associated to the formula that you show us?
There is actually, yeah, and so this has a lot to do with the third thing.
I see.
So there's so associated to this, yeah, I was it'd been good if I could have, see my font's getting smaller the higher I kept zooming in as I went. So the answer is yes. So I can take this sum, and I can sort of break it down into a sum over dict paths. And so what this dict path is there's for each k, I can associate a dict path to the pair of m comma a, and it's the dict path with the property that there's a box under the path at ij, precisely when ij contributes to this dinv kind of thing.
Okay.
Yeah, to this dinv. And so I can therefore break this guy down. And so that's where these dict paths appear. And so when you do this, and I will explain this next time, you can write this as a pair of sorted M and A, and then the unicellular LLT polynomial associated to that particular path. So you get X of A out here, and then the unicellular LLT in the Y variables. And so, yeah, you kind of, this is how, I mean, so like I was saying that you can recover, for instance, the original, the shuffle theorem from specializing this guy. And so this dick path that appears. That's how you get the dick path in that way.
I see.
And also I'll just preview next time. So what I said this relates to this thing which is the Hessenberg paving of this affine Springer fiber. So Hessenberg function is this extension of the Springer fiber, where you have an input, which is this Hessenberg function, which is the same combinatorial data as a dick path. And so this expansion, in fact, is related to a paving of this space into subspaces which look like vector bundles over certain type of Hessenberg variety associated to that very same dick path. And so that's a parallel. You can see the combinatorics is explained by this. This is the geometric explanation for that combinatorics, and this has to do with the fact so that there's the result of oops. So by Shereshian and Wax paper, the LLT polynomial computes the equivariant cohomology of the Hessenberg variety, and so that appears for the same reason that this is break. It's the same thing.
I see. Thank you. Any other questions? If not, then we'll see everyone on Thursday. Thank you. Bye.